Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. All right, lesson 13, tides, sound waves, the stock market. Classwork opening exercise. Anyone who works on or around the ocean needs to have information about the changing tides to conduct their business safely and effectively. People who go to the beach or out onto the ocean for recreational purposes also need information about tides when planning their trip. The table below shows tide data for Montauk, New York for May 21st and 22nd back in 2014. The heights reported in the table are relative to the mean lower low water, MLLW. The MLLW is the average height of the lowest tide recorded at a tide station each day during the recording period. This reference point is used by the National Oceanic and Atmospheric Administration, NOAA, for the purposes of reporting tidal data throughout the United States. Each different tide station throughout the United States has its own mean lower low water. High and low tide levels are reported relative to this number. Since it is an average, some low tide values can be negative. NOAA resets the mean lower low water values approximately every 20 years. Okay, so if I look at this here, it is on May 21st and 22nd. It's a Wednesday and a Thursday. And these are the dates or the times and the height in feet. And notice this negative height. So the reason for a negative height just means that it was lower than the mean or the average in that 20-year period. Okay, so there's the data we're going to use on the next page. Okay, so on page 2, part A says to create a scatter plot of the data with the horizontal axis representing the time since midnight on May 21st and the vertical axis representing the height in feet relative to the MLLW. So the first thing I'm going to do is label my axis. Okay, so let's just pick a color here and horizontal axis representing the time since midnight. So down here, horizontal. I'll just put it over here so it's not out of the way. It's out of the way. Time since midnight. And over here, it is height in feet. Okay, so now I brought in the table from the prior page down here, and we will graph it. So starting at midnight, it is 0, 0. 2:47 a.m. would be, here's 3. 2:47 would just be to the left of that. And it was 2.48. So here's 3. So it'd be about here roughly. So that's this data. Okay, continuing on, 9:46 a.m. is, here's 9. So it's partway between 9 and 10. Negative 0.2. Negative 0.02. So about there. And then at 3:31 p.m., 12 plus 3 is 15. That'd be 15:31 military time. So 3:31 p.m. is 15:31. And it should be right around here. And it's 2.39. 2.39 is way up here. And actually, I think I would put this dot in the wrong place. It's 2.48. Let's move that up to 2.48, which would be about here. All right. So continuing. Wednesday, we're still in Wednesday, 10:20 p.m. Adding 12 would be 22:20. 22 is here, 23 is here. So in between the halfway point, somewhere around here, it is 0.27. 0.27 would be way down here. Okay. Thursday, May 22nd, 3:50 a.m. Well, midnight would have been 24 hours after the previous midnight. 24 plus 3 is 27:50, almost 28. Just shy of 28 to 2.3. So here's 28, here's 2.3, just to the left of it, right about there. Okay, 10:41 a.m., 24 plus another 10 is 34.4. 34 is over here, 0.02. 0.02 is almost 0 right there. 4:35 p.m., 24. 4 p.m. is 16 in the military time. 24 plus 16 is 40. So it's 40 hours and 35 minutes after the first midnight on the 5th. Okay, so 40, 35. So halfway between 40 and 41 and 2.51. So way up here, 2.51 would be about here. Okay, and then finally 021 would be 48 hours and 21 minutes. That's 11:23 p.m. That is only a half hour before 48. So it'd be 47 and a half, which would be about here. And it's 0.21, which is down here. Okay. So remember, these are tidal heights. So the water's got to come down to this point here and then turn and come back up like so. And then it's got to turn and come down, turn and go up. So the tides are getting higher and lower and higher and lower. Oops, let's get rid of that. Okay, and then lower again. So there's the graph sort of the tidal heights. Can't really go backwards there. That's better. Okay, so that's a sort of what the graph would look like after graphing all those points. Okay, so part B says, what type of function would best model this set of data? Explain your choice. So even though the maximum points don't have the same values, the sinusoidal function would best model this data because the data repeat the pattern of high point, low point over fairly regular intervals of time, roughly every 6 hours. Okay. All right, page 3 says example 1, write a sinusoidal function to model a set of data. A, on the scatter plot you created in the opening exercise, sketch the graph of a sinusoidal function that could be used to model the data. So I will go back to that page and I have brought in one that has all the data points labeled and an approximation of the graph so that it is sinusoidal, so that it does have the same height at every period or interval of the period. Okay, and so there it is. That's part A. Part B says, what are the midline, amplitude, and period of the graph? Okay, so to find the midline, first thing I'm going to do is choose a dash line. Okay, and how about, I don't know, red. So if I choose a midline, well, it's got to be halfway between the maximum and the minimum. The way this is drawn, the minimum is 0. The maximum is 2.5. Half of 2.5 is 1.25. So it would be approximately here. Maybe up a little bit more. Okay, right about there. So there is my midline. And how about I label it? Y equals 1.25. There's my midline equation. Okay, so midline. Amplitude. Oops, wrong way. All right, so amplitude is how far up it goes and how far down it goes. The amplitude here is, it's going from 1.25 to 2.5, which is a distance of 1.25. And this is a distance of 1.25. So therefore, the amplitude is 1.25. The period of the graph, okay, I keep going the wrong way, back here. The period of the graph, okay, well, if we started right here, up to a maximum, actually, no, let's not start there. The sine graph starts at, let's start at the midline. So let's say we started right here. Up to a maximum, down to a minimum, and back up to a maximum is one period. This right here is one period. And it started at almost 0, and then it got to 12, just shot, or a little more than 12, but we started a little more than 0. So the distance from here to here is 12 hours. So the period is 12 hours. Okay, part C, estimating the horizontal distance between a point on the graph that crosses the midline and the vertical axis. The distance between the vertical axis and the midline point. So what they're saying here is if I had a point on the vertical axis right here, the distance from a point on the vertical axis to the midline, a point on the vertical or on the horizontal distance between a point on the graph that crosses the midline. So here's a point on the graph that crosses the midline and the vertical axis. What is that distance? Okay, and it looks like it's about 12 and a half hours. So 12.5 hours. All right, D, write a function of the form f of x equals a sine omega x minus h plus k to model these data where x is the hour since midnight on May 21st and f of x is the height in feet relative to the MLW. Okay. All right, so f of x equals, okay, so what is A? A is our amplitude. Move back up here, amplitude was 1.25. Sine, what is omega? Okay, what we need to remember is that the period, let's just say P, I changed it to blue wire, blue. The period is equal to 2 pi over the absolute value of omega. And we want to know what omega is. So to solve for omega, we just have to rearrange this. So omega equals 2 pi over P, our period. Well, the period is right here, it's 12. So omega equals 2 pi over 12. Okay, I could simplify that to pi over 6. So 1.25 sine omega is pi over 6, x minus, and h is our horizontal phase shift. So if I go back here, how much did it get shifted? Okay, and that is this right here. The horizontal distance between a point on the graph that crosses the midline and the vertical axis. Let's just say it's 12.5 hours. So it's 12.5 plus some k. Well, k is our midline, and our midline was 1.25. So here is the equation of our sinusoidal function that represents the the height in feet of the tide. All right, page 4, exercise 1 says the graph of the tides at Montauk for the week of May 21st through the 28th is shown below. How accurately does your model predict the time and height of the high tide on May 28th? So if we go back to our graph, the high was like 2.5 and it went down to 0 approximately. Okay, this one, so if I drew a line at 2.5, there it is, and a line at 0, there it is. What's our prediction now? Okay, so here it looked pretty good, but then all of a sudden the tides were going higher and higher and higher and higher, and we're off by it all went all the way up to almost 3 feet. Okay, so to answer that now, we would say the maximum value of F is 2.5. The high tide on May 28th was almost 3 feet above the MLLW. The model is off by approximately 6 inches. All right, page 5, example 2, digital sampling of sound. So back in the day, they used to record music onto cassette tapes. And then it went to records came first actually, then cassette tapes. And then we went to CDs, and then compact discs were digital. And then finally, now we're MP3s and that kind of thing. So let me just read this little tidbit to you before we start example 2. It says, when someone hears a musical note, their eardrums are sensing pressure waves that are modeled by a sinusoids, or combinations of sinusoids. As the amplitude of the wave increases, so as the amplitude of the wave increases, the notes sound louder. So that's your volume. Amplitude is your volume. So if it's really short, it's really low, quiet. As the frequency of the wave increases, which means the period is, okay, as the amplitude of the wave increases, the notes sound louder. As the frequency of the wave increases, which means the period is decreasing, the pitch of the note increases. A pure tone of the note A has a frequency of 440 hertz, which means the graph of the sinusoidal function that represents this pure tone would complete 440 cycles in 1 second. So if you look at A right here, if this was the note A, it would do this. It'd start here, go up to a maximum, actually it'd start here, go up to a max, back down to here, down to a minimum here. So it would make this wave 440 times in 1 second if it was an A note. The higher you stretch it up, the louder it is, okay? So it says the function would have a period of 2 pi over 440 seconds. If the sampling rate increases, the sound quality improves. To avoid distortion of the sound that is perceptible to the human ear, a sampling rate must be used that is more than twice the frequency of the tone. All right, a lot of people are now lost on that concept right there. A lot of people crank their tunes way up so loud that there's distortion and it sounds horrible, but they're trying to impress you by showing that they like to listen to things loud, I guess. But it's just distorted mumble jumble. So to avoid distortion, the sound that is predictable to the human ear, a sampling rate must be used that is more than twice the frequency of the tone. If the resolution increase is represented by the vertical scaling, the quality of the digital sample also improves. In reality, analog sounds are converted to digital sounds at a sampling rate of thousands of times per second. A typical resolution is 16-bit, which means the difference between the highest and lowest values are divided into 2 to the 16th equal sections. And the actual tone is assigned to the closest of those values at each sampling point. This example is simplified using a much lower sampling rate and resolution to allow students to understand the concept and keep the total number of data points manageable. Okay, so now it says here, when sound is recorded or transmitted electronically, the continuous waveform is sampled to convert it to a discrete digital sequence. If the sampling rate represented by the horizontal scaling or the resolution represented by the vertical scaling, increases, the sound quality of the recording or transmission improves. The data graph below represent two different samples of pure tone. One is sampled 8 times per unit of time at a 2-bit resolution, 4 equal intervals in the vertical direction, and the other is sampled 16 times per unit of time at a 4-bit resolution, 16 equal intervals in the vertical direction. Which sample points would produce a better model of the actual sound wave? Explain your reasoning. Okay, so you'll get a better model with the sample points in figure 2. Figure 2. If the function we use to model the data passes through more data points on the original sound wave, the curve we use to fit the data will accurately represent the original sound. Okay, page 6, part B. It says to find an equation for a function g that models a pure tone sample in figure 1. So I brought over the graph. This is sample 1, figure 1. So here's the equation of the sine function. So we need to know what amplitude is. So I would just make a list over on the side first. Amplitude is the distance from your midline to your maximum, or your midline to your minimum, which is equal. So the first thing I'm going to do is I'm going to draw my midline. The midline is halfway between the max and the min. Well, the maximum here is 16 and the minimum is 0. So the midline is 8. Okay. So y equals 8 is my k actually. I'll get to that in a minute though. So A, amplitude, is how far up it goes from the midline. So from 8 to 16 is a distance of 8. So A is 8. Omega, remember from the prior page, what's omega? Let me go back 3. Omega is 2 pi over the period. Okay, so omega equals 2 pi over the period. The period, if we were to start here at 2, go up to a max, back down, down to a minimum, back up, 14 minus 2 is 12. So 12 is my period. So omega equals pi over 6. And if I use my calculator, I could leave it as pi over 6, I suppose, but what's pi over 6 as a decimal? 0.523, something like that. Okay. I'm just going to leave it pi over 6. What is our shift? Well, if we wanted to start right here instead of here, from 0, it got shifted over almost 2. I'd say approximately 1.8, I guess. So H equals 1.8. All right, and K, well, if this should be down here at 0, your Y equals 8 is your K, K equals 8. So now my function g of x is going to equal, an approximation of course, 8 times the sine of omega, pi over 6. I'll just leave it in terms of pi. You could also have used the decimal, 0.5236, pi over 6 times x minus h plus k. Okay, so part C says to find an equation for a function h. So h of x equals. All right, so on this one, what's our midline? Let me grab a dash line with arrows and make it red. Here's my midline. It is at 8. right there. Okay, maximum is 16, minimum is 0. So our midline is 8. So A equals 8. Omega is going to be, again, 2 pi over p. And what is our period? Well, our period is starting right here at, that's just shy of 2. Let's say it's 2. And it ends, max back down to 0, minimum back up. It ends right there at 14. So the period is approximately 12. So that would be, again, be 2 pi over 12 or pi over 6. So omega equals pi over 6. H, phase shift, looks like it's about 2. I'll put 2. It's a little bit less though, so let's just take a look here. Let me erase that. So 2 would have been here. It's over here. Let's say it's 1.5. Let's make H 1.5. And then finally K, and this would be off a little too, of course, because 1.5 and this ended up being approximately 14. So I'd actually say that that would be 14 minus 1.5 would be 12.5 instead of 12. Okay, but this is close enough for now. And let's see what's K. K is our midline. K is 8. So there's our equation. H of x equals 8 times the sine of pi over 6 times x minus 1.5 times 8. Okay, exercises 2 through 6. Stock market, stock prices have historically increased over time, but they also vary in a cyclical fashion. They don't just go up, up, up. They go up a little, then they go down a little, and then they go up some more, and then up a little more, and then down. So it says to create a scatter plot of the data for the monthly stock price for a 15-month time period since January 1st, 2003. So here's January 1st, 2003, month since 0, that'd be January 1st, February 1st, March 1st, and so on. Once a month. Okay, so we're going to create this in the calculator. In order to do a scatter plot in a calculator, just turn your calculator on, be on the home screen, clear it, press the stat button, and under edit, number 1 is edit, so you hit enter. Under L1, I'm going to put the month since, and under L2, I'm going to put price at close in dollars. So this is just simply going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so you should have 15. So if you put the cursor on here, it tells you in parentheses how many data values you have. 1, 2, 3, 4. Obviously, if you're starting at 0, and the last number is 14, there's 15 entries. Or arrow over and plug in the next column. 20.24. Whoops. I hit enter instead of point. 20.24. 19.42. Oops. Okay. 18.25. 19.13. 19.2. 20.91. 20.86. 20.04. 20.30. 20.54. 21.94, 21.87, 21.51, 20.65, and 1984. Okay, so when you're done, just make sure you have same number of L1s as you do L2s, or when you go to do a data calculation, it is going to say error mismatch, which just means your X values do not match your Y values, and they have to. Okay, so now I'm going to hit stat. Actually, I'm going to hit graph, and I'm going to go to Y equals and make sure there's nothing there. And when I hit graph, you don't see anything. So I'm going to hit zoom 6, which puts it back to 0, 0, and I still don't see anything. So if I hit, if I hit zoom, there is a stat command down here at 9. And if I hit zoom stat, it still doesn't show. So you go to stat, there's the data, and graph. Zoom 9, enter. Why is that not graphing? Okay, I didn't turn my stat plot on. So I've got to go here. I got to go up and hit plot, and I have to turn my stat plot on. Now if I hit graph, it should be there. Zoom 9. There it is. Okay. So this doesn't look right. So if I hit trace, we're at 0, 20.24, 1, 19. I must have a data value entered incorrectly. Yes, I do not have a decimal for 20.86. So if I go back to my calculator and hit edit, okay, I see it now. So if I come down here, I did not hit the decimal. So a 2086 stretched it way out and it put all my data values wrong, or not wrong, but the window was messed up. So now if I graph it and I hit zoom 9, it should fit, and there it is. Okay, so let's recap. Enter the data, stat, edit. First column is L1, second column is L2. Go to Y equals, turn your plot 1 on, or you could also go to second stat plot right here, hit enter and make sure it's on. You want it a dot plot type, which is right here. This is squares. We could have had pluses or just simply dots. And then when you hit graph, it will, and then you hit zoom 9 for zoom stats. So there's the graph right there. All right, so then the next part says, would a sinusoidal function be an appropriate model for these data? Explain your reasoning. So I look at this and I don't really see a sinusoidal function. So I'm going to say no, that a sinusoidal function would not be appropriate because the data are trending upward as time passes. Okay, it is kind of going up from left to right. It's kind of tipped. So this value here is obviously not, it didn't come down to this low. So it's going higher highs, higher lows. So therefore it is not sinusoidal. All right, page 7 says we can model the slight upward trend in these data with a linear function f of x equals 19.5 plus 0.13x. So I open up my calculator and I put that in under y equals. So 19.5 plus 0.13x is right here. And then when I graphed it, I got this graph right here. So I copied it over to the screen here. So that's how that occurred. So here was our scatter plot. And then they gave us this linear function. Now, if I look at this and rotate it so that that linear function is horizontal, that would be my midline. So then if I were to graph this and draw a function now, it looks like the top's about here and the bottom is about here, and that's the midline. So this thing is sort of, this thing is sort of going like so. Okay, obviously it's not a perfect fit, but you can see that that now appears to be somewhat sinusoidal. These are a little bit higher than they should be, and the midline's not quite centered between. Okay, but this gives us an idea. So it says find a sinusoidal function g that when added to the linear function f will model these data points. So what function would give us this? So if I go to my calculator and I hit trace, this point right here is 0, 20.2. We knew that from our table, by the way. So our y-intercept, or our y value at when x is 0, y was 20.2. My linear function is 19.5 plus 0.13x. So 0.13 is the slope, and 19.5 is the y-intercept. So from 19.5 to 20.24 is approximately what? 19.5 to 20 is 0.5. And then another 24 is 0.74. So it looks like it might go a little bit higher than that. That wasn't our high because my line is up here more. So let's just say that's, I don't know, 1.1. So let's say g of x equals, and our amplitude equals 1.1. So it's going to be 1.1 times the sine of, and what is our omega? So if I go back to my graph here, well, omega, what's the period? Remember that omega, the absolute value of omega equals 2 pi over our period. The absolute value of omega equals 2 pi divided by our period. So if we find our solve for our period, we would get our period to equal 2 pi over the absolute value of omega. So our period equals 2 pi over what? So if I go back to my calculator, our period looks like it starts here and ends up, back down, minimum, back up, right here. Or we could use this one from here, down there, up there. And there's points near both of those. So I want to know what this point is. This point is 1, 19.42. So I'm going to write that. 1, 19.42 is this point right here. And if I go down, stop, up, stop, then I would want maybe this point right here. So if I go back to my calculator and arrow over to the right with my tracer, it's going to bring me to that point right there, which is 7, 20.04. Okay, so the change in my x was 6. So from here to here is a distance of 6. Okay, so if that were 6, that's going to be my period. So let's change that p to 6. Okay, so what I want to do now is solve for omega. So just move that 2 pi over here and we get omega equal to 2 pi over 6, oops, or pi over 3. And what is pi over 3? 1.04, or let's just leave it like that, 2 pi over 6. Okay, so that is our omega, 2 pi over 6. Hopefully you followed that. 2 pi over 6, parentheses, x minus, and our shift is to here. The sine function starts at 0 on this line here, but it's shifted over to here. And that value is approximately what, 4? Let's look. Go to graph, trace. And we are somewhere over here. Yeah, so it's right around here, which is 4. So I would put a 4 here for h. H equals 4. And then finally, what is our shift up? Well, in this case, we're going to use our midline as our starting point, so I won't have a k. It's not shifted up or down, or we could. Our midline is at an angle though, so let's just leave k alone and make that our center as 0. So there would be g of x. Okay, this is just an approximation, something close to that though. All right, page 8, number 4 says to let S be the stock price function, that is the sum of the linear function listed above and the sinusoidal function in exercise 3. So what we're going to do is go back here and just add this to that. So 19.5 plus 0.13x, 19.5 plus 0.13x plus, and then our sinusoidal function, 1.1 sine 2 pi over 6, 1.1 sine 2 pi over 6 times x minus 4, close parentheses. Okay, let's make sure that was it. Let's see, yes. Okay, so there's the equation. Now it says add the graph of this function to your scatter plot. How well does it appear to fit the data? So I'm going to go back to my calculator. I'm going to go to y equals, and I'm going to put this function here. Actually, I could just put it up on this line here and just hit plus 1.1 sine 2 pi divided by 6 times x minus 4. And then graph it. How well does that fit? It fits pretty good. It's not too bad. So there's the graph of that function. How well does it appear to fit the data? Okay, so the scatter plot with the function S is shown below for the first 15 months. Let's see. In general, it appears to model these data points, but there are a few outliers, such as stock value 2 months after data were reported. Okay, so that one's off a little bit. There's some that are off. Okay, so now it says here is a graph of the same stock through December of 2009. And by the way, this is Microsoft. So if you go into any program that shows a graph of stock prices, this is Microsoft's actual price values. So A says, with your model, will your model do a good job for predicting stock values past the year 2005? So here's March 2005, and then here's what happened here. So 2008, there's a big dip, and February 2009, it rallied back up. So will it do a good job? The answer I would say is no, it's not going to fit after that. It was sinusoidal here, kind of right here. All of a sudden it got wacky and went outside of the amplitude. So in words, it will not do a very good job of predicting the value of the stock because it rises sharply and then plummets before starting to rise in price after a low in 2009. B says, what event occurred in 2008 to account for the sharp decline in the value of stocks? Well, let's see, 2008, this is 2021. 21 minus 8 is 13. So you're what? If you're taking Algebra 2, 3 years old or 4 years old at the time. Do you remember what happened in 2008? Okay, there was a financial crisis in the stock market, mostly in the housing department. The housing kind of went crazy. A bunch of loans were, what banks were giving out loans to people who couldn't pay them. They were taking out ARMs, which is adjustable rate mortgages, and then the interest rate went way up, and then that did not allow people to afford their mortgage anymore, and all of a sudden people were going bankrupt and they couldn't pay their mortgages and their houses were getting repossessed. So that was what happened in 2008. It was a financial crisis in the market, so let's bring that in. And there was a financial crisis in the stock markets that marketed the start of a recession. That marked. C, what are the limitations of using any function to make predictions regarding the value of stock at some point in the future? All right, there are many variables that can affect the price of a stock. A function that is based only on time will be limited to its ability to predict future events during unforeseen circumstances. Okay, so nothing is perfect. Okay, page 9 brings us to the end of lesson 13. Review the lesson summary and go to your problem set.